Hello, this is Paul from Foresight Tech. In this video, let's prove Theorem 3.1.2, which is additional properties of vectors in n space. In the previous theorem, we proved some basic properties, right, in n space. So here is the additional. We have three. See, all these are straightforward. Okay, so the first zero is a scalar number 0. So 0 scalar number times v equals 0 vector. Okay, so keep in mind. Second is a vector. And this is scalar, which is scalar multiplication. So this should be a 0 vector in space. The second is all vectors. Okay, so this is vectors. And so let's just look at the letter C. So we take a little bit time, and the A is superficial, right? Because it's 0 scalar multiplication, by the definition, we should get all 0. And the B is also scalar multiplication, so we also, by the definition, is to get a 0. Oh, so that's simple to put down here. So first of all, A, 0 times a vector. No matter the vector is what, see. So let me say 0 times a vector, v1, v2 to vn. And therefore, by the definition, see, by the definition of a scalar multiplication, so it equals 0 times v1, 0 times v2 goes to 0 times v, and each is a scalar is just a multiplication of scalar numbers, so equals 0. So this equals 0, 0, 0, which is a 0 vector. So that's for A, and then B is almost the same. So let's look at the B. So K is a scalar number times the 0 vector, which is K times 0, 0, go to all 0. By the definition, the first is K times 0, and then K times 0 the second, and then goes on K times 0 the last. Of course, what do we get? We definitely get all 0, right, which is the same, so 0 vector. And the last C, okay, and then the first is scalar multiplication, and the second, to remember the definition, so what is this? Negative v, we call the inverse. This we call inverse or negative of a vector u. By the definition, so inverse, the definition of inverse means v plus the inverse vector should back to the identity, which is 0 vector. That's the definition. Okay, so now it says the inverse of v is just the scalar multiplication. Okay, the vector v times -1 scalar multiplication. Is that true? Yeah, definitely. So we exactly know the inverse should be each coordinate or each component go to negative, right? And the scalar multiplication and also each component goes negative. Okay, so straightforward. Or we can verify. So let's just verify by the definition. Let's just verify. See, we say so given v, and then the inverse v equals -1 times v. Okay, so we need to prove why. The inverse is just a scalar multiplication by -1. I do this way to prove. Okay. So we work on the definitions that upon this vector plus the vector v. See, do you think -1 times v plus v equals 0 or not. If these are put together equals 0 vector, so -1 times v should be the inverse, right? It is definitely. Okay, so we can do this. So this is a -1 times v, and this is 1 times v, right? Okay, because what? Because 1 is identity. Okay, see, 1 is identity. 1 is identity of so this is scalar number 1 of scalar multiplication. Okay, so that's true. And one more. See, this should be equals -1 plus 1. Is that okay? And then times v. The previous theorem. So distributor. Remember distributor. This is from the previous theorem 3.1.1, basic property of a distributor. We put it together. Okay, so this what? This is just 0 times v. Yeah, see, 0 times v vector 0 times v equals 0, right? A, we already proved. So this equals 0 vector. This is just from part A. Yeah, that's good. So what do we get? We get this term. See, this term should be the inverse of v, right? So therefore, so by the definition, okay, by definition, this is by definition, -1 times v should be equals the inverse of the negative vector. That's all. Thank you.